Welcome, everybody. It's my pleasure today to introduce Yuzhou Chen, and he'll be telling us about topological relational learning on graphs.
Okay, so I think I can start now, right? So, hello everyone, this is Yuzhou Chen, and I'm currently a postdoc at the Princeton University. And today I'm talking about our paper, Topological Relational Learning on Graphs. And this is a joint work with Barry Scott Gunnar and Yulia Gale. So first, let me give a brief introduction of our work. So as we know, although the geometric deep learning GDL achieves the highly competitive performance in the various graph-based classification, for example, like the node classification and the graph classification, and some prediction tasks, for example, like the link prediction, regression, and the forecasting. So it is often found to be vulnerable to the graph attacks and other stereo perturbation. Okay. And most GDL tools on the graph learning, for example, like the GCN-based model, no matter it is on the spatial domain or the spectrum domain, so they only access the global graph topology, and they only look at the immediate or the first order neighboring nodes for aggregating the graph topological information and updating the features of the target node. And thus it tends to suffer from either the overfitting or the over-smoothing problems. So to address these above limitations and drawbacks, so in our paper, we propose a new topological relational inference. This is a framework which allows us to learn a local graph structure systematically, and also it can help integrate the high order interactions into the graph neural network framework efficiently. And therefore, finally, it can enhance the robustness against the graph attacks and the perturbations. And here we list the key contributions in our paper. So first is we proposed a novel graph learning framework by revising the graph neural networks. So based on the idea of the similarity among the shapes of the local node neighborhood. And the second is we developed a novel topology-induced multi-graph representation of the graph, which is the core part in our proposed model. And it can account for the key local information on the attributed graphs. And also it will serve as an important remedial component against the perturbation and other adversarial attacks. And then lastly, we derive the theoretical stability, which guarantee for the new local topological representation of the graph. And we also discuss their implications for the graph algebraic connectivity. And in our paper, the ultimate goal here is to bring the information on the local persistent homology from each node neighborhood into the graph learning procedure. So now let's see the first part in our proposed GNN model. So that is the topology-induced multi-graph representation. So if we wanted to define a topological similarity among two node neighborhoods, so first we need to extract all the n-dimensional topological features, including like the circles, cavities, or more general n-dimensional holes. And then we can compare the node neighborhoods in terms of their exhibit shapes. So first of all, we need to extract the weighted k-hope neighborhoods. So suppose given a graph G and the target node is a node U, and its weighted k-hope neighborhood is an induced subgraph with an edge weight function tau induced by a similarity of the node attribute, if and only if the following two conditions are satisfied. So first is for the any node V which belongs to the k-hope neighborhood of the node U, the shortest path between node U and node V is at most k. And then the second is suppose there are two nodes V and W which belong to the k-hope neighborhood of node U, and also there exists a connection, so that is an edge between the node V and node W. Okay, and then based on the edge weight function tau, we can get their edge weight between the nodes V and W, which is denoted by the tau VW. And in this equation, the xv, xw are feature vectors for the nodes v and w respectively. And the norm function can be either the Euclidean distance in case of the continuous node features, or the Hamming distance in case of the categorical node features. So in order to compute or measure the shape similarity of the two K-hope neighborhood subgraphs, for example, like the GOK and GVK. So that is we're interested in these two nodes. So this question is equivalent to comparing their corresponding persistent diagrams PDs. And as we know, the persistent diagram is one of the popular topological summaries. Okay, so where each topological feature is denoted by a point in the x and y coordinate, and the x-axis represents the burst time, and the y-axis represents the death time. And the persistent diagram can help us track how the topological feature appear and disappear in a nested sequence of the topological space. So now, based on the definition of the weighted K-hope neighborhood, and suppose our target nodes are the node U and the node V, and then we can, based on the and equipped with the persistent homology, we can extract their persistent diagram, so that is the DGOK and DGVK, and then we can measure the topological similarity between these two subgraphs with the Watson distance between their corresponding persistent diagrams, which is defined as follows. Well, in our practice, the we set the P equals to 1, so that is we consider the Watson 1 distance. And also it was to mention, so the more similar two subgraphs are, the smaller of the Watson distance is.
Can I ask a quick question?
Sure.
So if you're working with graphs, so there's going to be 0 and 1 dimensional persistence, but won't there be a lot of infinite persistence if there's no two simplices?
You mean that if there are no simplices, how we will deal with this error, right?
Yeah, I mean, are you using extended persistence, or how do you deal with the infinite points, I guess, in this calculation?
Oh, so here we consider using the VR complex, and the filtration we consider using the based on the node attributes and the node degree.
So it's not just a graph.
Yeah, sorry, but we're working on the graph.
But they're taking the click complex of the graph. So if you have 3 edges, you throw in the triangle, I think. Yeah.
Right, yes, right.
Thank you so much for the clarification.
Yeah. Okay, and to better illustrate how the topological similarity, so that is the Watson distance, is computed between the two persistent diagrams from the two subgraphs GOK and GVK. So here, let's see a talk example showed in the figure 1. So suppose that the target nodes is the node U and the node V, and we have their corresponding subgraphs. So that is a K-hope, a weighted K-hope neighborhood GOK and GVK, and based on the equivalent with the persistent homology, we can choose one filtration function, and we can get their corresponding persistent diagrams. Okay, and then we apply the Watson distance function on these two persistent diagrams. We can get the topological similarity between two nodes. So armed with the K-hope neighborhoods and the persistent diagrams and the Watson distance, so now we can generate the topology-induced multi-graph representation. So given a graph G and with the Watson distance as a measure of the topological similarity among two K-hope neighborhoods, GOK and GVK, so that is for the all nodes U and V belongs to a set of V. And then the topology-induced multi-graph representation of the G can be defined as the omega, so which consists of a set of nodes V and a set of multi-edges E top. So the definition of E top is defined as follows. And from this equation, we can see the E top, so that is the multi-edge, consists of 3 components. So the first is the information from the original graph structure. So that is the edge information we can extract from the original adjacency matrix. And the second component is represents the information from the topology induced, from the positive topology induced adjacency matrix. Okay, so that is we assumed the element WUV top plus equals to 1 if the Watson distance between two subgraphs from the node U and node V is less than the predefined threshold epsilon 1. And the third component represents the information from the negative topology induced adjacency matrix. So that is, we assume that the element WUV top minus equals to -1 if the Watson distance between two subgraphs from the node U and node V is larger than the predefined threshold epsilon 2. Okay, and also compared with the regular edge set, the multi-edges consist of both the graph structure and the local topological information, right? And the intuition behind the topology-induced multi-graph representation is to reflect a level of the shape similarity among any two node neighborhoods, regardless whether there exists an edge or connection between two nodes or not. And in the practice, to store this topological, the multi-edge information, we use the tensor W, and we let the WUVR be the R type of the edge between the nodes U and V. So you can see the subscript here is node, so U and V represents the node indices, right? And R is the types of the edge. And when I equals to 1, so which represents the edge information from the adjacency matrix. When I equals to 2, so which represents the edge information from the positive topology induced adjacency matrix. And when I equals to 3, which represents the edge information from the negative topology induced adjacency matrix. And finally, we consider joint topology induced adjacency matrix, W top. So that is, we will do a summation along the type of edge channel. And if the summation is larger than 0, we will say there exists a connection between the node U and the node V. Otherwise, there's no connection, no edge between node U and node V. So that is the rationale behind that is, so if two nodes, they are topologically similar, so we can add an edge between them, despite there is no any connection in the original graph structure. However, if two nodes, they are topologically dissimilar, so we can remove the edge if the edge exists in the original graph structure. And to better understand the implementation of the topology-induced multi-graph representation in our experiment here, let's see a talk example showed in the figure 2. So suppose the target node is node 1, and we consider its one hop neighborhood. So that is node 2, 3, 4, 5, 6. Okay. And based on the conclusion from the topology-induced multi-graph representation, so first we can compute the Watson distance, so that is topological similarity between two nodes. So for example, node 1 and node 6, and the Watson distance is 0.1. And also we define the threshold epsilon 1 equal to 0.5 and epsilon 2 equals to 2. And in this case, we can find the Watson distance between nodes 1 and 6, which is less than the threshold epsilon 1. So we can think this, so we can think these two nodes, they are topologically similar, and that we can add an edge between them. Okay, and let's see another case. So that is between the node 1 and node 2, the Watson distance is equal to 3, which is larger than the threshold epsilon 2. And then we can think these two nodes, they are topologically dissimilar. That we will remove the edge between them, despite there exists a connection between them in the original graph structure. And finally, we will do the summation along the type of the edge, and we will get the W top. So this is the output from the topology-induced multi-graph representation framework. So next is the STEM framework. So, so that is the second part in our model. So in our paper, we also propose a new recursive feature propagation scheme, STEM, so which updates the node features from the subgraphs, topologies, and the attributes of the neighborhoods. Okay, where the subgraphs and topology information will come from the topology-induced multi-graph representation framework, and the attributes of the neighborhoods will come from the node feature vectors. Okay, and so for example, for the node U, we can update its feature representation by using the set information collected from the nodes within its K-hop local neighborhood. And the T10 iteration is formulated as follows. And in this equation, where the F up is the update function, which can be the MLP or other gated function. And the phi function here is the aggregation function, which aggregates the topological feature into the node features. So it can be the sum or the average. And the DUV hat is a normalized reciprocal topological edge weight. So we can say in the numerator, it represents the what's the distance between two subgraphs from the node U and node V, right? And we do an inverse here. So that means the more similar two subgraphs are, the higher of the topological edge weight DUV hat is. And also we set a weighting factor alpha U. So for example, we can image in the power network. So the node as the generator will always plays an important role in the power flow transmission or the architecture design, etc. So we may assign a higher weight to this kind of nodes in the network.
Yuzhou, let me interrupt with a question if that's okay. So in the chat, somebody asks, how do you fix the parameters epsilon1, epsilon2, and k from the K-hop neighborhood? Any suggestions there?
Yeah, so 1 second. So in the experiment, we set the epsilon1 and epsilon2, they are hyperparameters, and it will. So firstly, we will draw the histogram of the Watson distance, see the distribution of the Watson distance between any type of nodes in the graph, and then we will consider the different quantile. I mean, we will search the best epsilon1, epsilon2 within the certain quantiles. So through the cross validation, and for the k, in our practice, we consider k from the 1 to the 5. So the optimal one will be searched through the cross validation.
Thanks so much.
Okay, thank you. Okay, and figure 3 here displays the overview of the STEM framework for the node feature vector extension. And to better understand the STEM framework, let me give more details here. So suppose the target node is node U, and here we consider is the 2-hop neighborhood. So which includes the 4 1-hop neighbors, V1, V2, V3, and V4, and the 3 2-hop neighbors, W1, W2, and W3. Okay, and also for each node, it is equipped with a 3-component feature vector. And then based on the conclusion from the topology-induced multi-graph representation framework, we can get the Watson distance between two subgraphs from 2 nodes. And then we use here we use the normalized reciprocal topological edge weight, so DUX hat, where here the box can be any node of the 2-hop neighborhood of the node U. Okay, and in this talk example, the solid arrow indicates the weight during the 1-hop neighborhood feature aggregation, and the dashed arrow indicates the weight during the 2-hop neighborhood feature aggregation. So this is a basic procedure in the STEM framework. So now, armed with the outputs from the topology-induced multi-graph representation framework and the STEM framework, so we can start construct our own convolution-based changing layer. So given the joint topology-induced identity matrix W top from the topology-induced multi-graph representation, we can compute the topological distance-based graph Laplacian. So that is the L top. And also we consider apply the random walks on the W top, where the row here can be either integer or the fractional. So that is, we can consider both the regular random walk and the long range random walk. And then, as similar as the vanilla graph convolution layer, we construct the changing graph convolution as follows. So you can see the psi function here is the nonlinear activation function, okay? And the mu here is the regularization parameter. And the HL and the HL plus 1 is the input and output activations for the L's layer. Theta here is the trainable weight. And also to reduce the computational cost, we search the best maximum, we search the best, the number of the iteration, the best number of the power iteration steps, max I, so from within a range between the 1 and 10. And the figure 4 shows the detailed architecture of the whole GNN semi-supervised learning framework. And we can see the input is the original graph G, and the top row represents the topology-induced multi-graph representation framework. And the bottom row shows the STEM framework. And their outputs will be fed into the GNN convolution layer for the final task. So now let's see the computational complexity for our method. So for the n-dimensional positional homology calculation, the computational complexity will be the O of the m to the power 3, where m is a number of the barcodes in both PDs. However, in our experiment, we mainly consider using the zero-dimensional topological feature, since we found there's no significant gains for integrating the higher dimensional n. And the computational complexity of the computing the Watson distance between two PDs from two hope neighborhoods is the O of the n to the power 2 and d bar to the 3 times k divided by 2, where n is number of nodes and d bar is the mean degree of the target nodes. K here is the k hope neighborhood. So now let's see the experiments. So in our study, we consider the 7 small and moderate networks. So first is the citation networks, includes the widely used the benchmarks called ML, CiteSeer, and PubMed, where the node here represents the article, and the task is to predict the subject of the articles. And also we consider 4 synthetic pulse networks. So that is the IEEE 118 pulse system, Illinois 200 system, South Carolina 500 system, pulse system, and the Texas 2000 pulse system. And for these synthetic pulse system networks, so the node can represent the load transformer or the generator, and our task is to predict what type of node in the pulse system. And table 1 here displays the summary statistics of these 7 data sets. And table 2 shows the semi-supervised classification performance on the 4 synthetic power systems, and of our proposed GNN model and 14 derived baselines. And in our experiment, we consider 2 GNN variants. So that is the GNN A, so which is based on the node attribute as a filtration function, and the GNN D, so that is based on the node degree as a filtration function. And from the table 2, we can find our proposed GNN models always outperforms the derived baselines. Okay, and table 3 shows the classification performance of our proposed GNN model and the stellar baselines. And we can see on the Cora ML and the side cell, our model outperforms the stellar baseline by a large margin. And for the PubMed, our model also achieves a very competitive results. And moreover, in our experiment, we also evaluate our proposed GNN model on two relatively large network. So that is the OGBN product and the OGBN archive. So these two networks are publicly accessed from the Open Graph benchmark. Okay, and we can find for the OGBN products, there are more than 2 million nodes, and for OGBN archive, there are more than 100,000 nodes, right? And table 4 here shows the performance of our proposed GNN model and 4 stellar baselines. And the results indicate that our proposed model is able to achieve the promising and competitive results on the very large network.
And Yuzhou, could you remind me again what you're predicting here? Like, what's the task to predict?
Yeah, the task here is to predict. So, for example, for the citation networks, the node represents the articles, and we will predict, which subject of these articles. And for the poll system, we will predict what type of what type of the roles the node plays in the poll system. For example, like the load, the transformer, or the generator.
Thanks.
Just to be sure, these are all node level classification, right? Not the graph level classification.
Yeah, it's node level.
Okay, thank you.
One more question, actually. So you mentioned that you didn't get any improved performance in bringing in the one dimensional persistence over the 0. I don't know if you checked it, but suppose you just use one dimensional and not 0. Does that improve over the baseline at all? In other words, is there any reason to believe that there's some one-dimensional persistent structure?
Yeah, that's a good suggestion. So in practice, at the beginning, we consider both 0 and one-dimensional topological features, and we found that when we involve the one-dimensional, somehow it will make the results worse, will reduce the performance. So we don't include the one-dimensional feature in our model.
This is a tough question. Maybe there's no answer. Do you maybe have an intuition? I mean, you're working on big data sets. Why the correct topology to be using is 0-dimensional, not 1?
Yeah, I do agree. I think it depends on the sparsity or the higher order properties of the node. It may differ among the graphs. It may not have a certain answer, I guess. Yeah, but you will be interested.
I can make a remark here if you like. So for example, if you use the degree kind of filtration, so you take a node, let's say you take four hop neighborhood. So let's say you have like 40 nodes here. When you use degree filtration, you can think of it as a Morse function. You are putting the low degree nodes to the bottom, and then you are putting the high degree nodes to the top. So two nodes have similar shapes. If you position in the same way, and then when they are connecting in the 0 dimension, you can see that when they're connecting in the higher levels in the same in the similar positions, then we say they are same. When you put in the click complex one-dimensional features, you can say that you have definitely some infinite persistence there for some loops which are not closing up, but that makes a lot complicated in there, and then so you have to make a decision there. So we made the decision to not include this one-dimensional ones. In 0 dimension, you don't have this kind of problem. You can use extended persistence for sure, but this at the end of the day, we want to improve GNNs with the is persistent homology, and this works very well to understand the similarity of the shapes of the nodes here. I hope this answers this zero-dimensional, one-dimensional question.
Thank you.
Okay. Okay, thank you. So let's continue. So also to evaluate the robustness of our proposed change in model. So here we generate the perturbed graphs with two adversarial attack methods. So one is the meta attack, so which attack the graph structure by removing or adding the edges based on the meta learning. And the second is the random attack, so that is which perturb the graph structure by randomly adding the fake edges. And from the results showed in the figures 5 and 6, which demonstrated that our proposed change in model can always outperform the baselines across all the perturbation rates on both adversarial attack method. And also in our paper, we explore the boundary sensitivity. So we can see from the figures 7 and 8, which show the performance of the change in model with different threshold hyperparameter combinations on two power systems. One is the Illinois 200 power system, and one is the South Carolina 500 power system. For example, in the figure 7, so the sub-figure A displays the histogram of the Watson distance in frequency. I mean, can see the x-axis represents the Watson distance, and the y represents the axis represents the probability density. And the figures, sub-figures B and C shows the performance of the change in model with different threshold hyperparameter combinations, and similar as for the figure 8. And from the results show these two figures, which indicate our proposed change in model is sensitive to the threshold hyperparameters combinations. And so that means the optimal hyperparameter, the optimal threshold hyperparameter combinations. So that is epsilon 1 and epsilon 2. So they may differ among the graphs, which might depend on the sparsity and like the label rates and the high order properties and other information from the graph. And here is some discussion and future work. So in this paper, we propose a novel topological neural network framework of the topological relational inference. So by revising the graph neural networks, which is based on the persistent homology concept invoked within each local node neighborhood. And in the experiments, we can see the change in model can achieve the highly competitive results on the clean graphs. And also under the adversarial attacks and perturbations, change in model also shows its robustness properties. And in the future, the topological relational inference framework, it opens the multiple paths for the adversarial learning and defense technologies, which is can be based on the side topological information. Okay, thank you. This is my presentation, and thanks for your attention.
Thanks so much, Yuzhou. Let's briefly either unmute yourselves and applaud or use a little emoji.
Thank you.
And now we have time for questions. So Rolando, if you're able to unmute yourself, please unmute yourself and ask your question. Otherwise, I can try to do so for you. Oh, we can't hear you, Rolando. Okay, so let me ask this question. Have you considered using the topological information achieved with persistent homology to infer E1 and E2? I don't know what E1 and, epsilon 1 and epsilon 2, yes. I suppose.
Yeah, so, 1 second. Yeah, so, oh, sorry, can you say your question one more time?
Can you hear me now?
Yep.
Yes.
Okay. What I'm wondering is that you have considered to use the information gained with the topological construction. For example, when you use persistent homology to get the persistent atoms, if have you considered to use that information about the topological features to infer epsilons instead of considering fixed values in computed with the tuning process?
Yeah, I think the so how tune the epsilon 1 and epsilon 2 actually is from the what's the distance. So this information, right? So first we need, so after we extract the Venn diagram from any type of nodes, and then we need to draw the histogram of this. I mean the distribution of the Watson distance, and then we can start to tune the epsilon 1 and epsilon 2. So since we need to know the maximum and we need to know the minimum and maximum bounds for the distance, and then we can start tuning based on different quantiles. I'm not sure this can answer your question. Mm-hmm.
Okay, thank you.
Mm-hmm.
More questions?
I have another question, particularly about the experiment. So sort of two parts. So the first part is what do the feature vectors look like for some of those subject classification tasks?
1 second. So you mean how the feature vector looks like, right?
Yeah, what information is in there?
Okay, so for example, like the for the power networks, so the feature can be some, for each node, where the node can be the load transform or generator. So it can be some load information or the number of or the power flow which is passed through the node. So this kind of the electronic properties.
What about the my electrical engineering is very poor, so I'll ask. What about the PubMed or the CiteSeer?
For the citation networks, the the node feature can be the, I think it can be. Let me think. Can be the some categoricals that the articles in the published in the archive or the CiteSeer, etc. Since the node represents the article and the edge is the citation between two nodes. Yeah, and but as I know, the for the Coral ML and the CiteSeer, the features are categorical, but for the PubMed, the feature is continuous.
I see. So given that, the question is, and it's kind of an open-ended question. So one of the things that your methods do is infer edges that are there, or delete edges that shouldn't be there. Sort of, is there in terms of interpretability, what could you say about the local topology under this like feature? In other words, what does it mean to say that two nodes have a small Wasserstein distance in its persistence diagram? Does that map onto any like intuitive understanding of what it means for two articles to be similar?
Okay, so I see your question. So let me go to the... Yeah, so in our paper, we can to measure the topological similarity, we can based on two directions. One is based on the node attributes. So that is the like what we mentioned before, like the attributes for each article, for example, in the citation networks. And another way is based on the node degree. So that is purely based on the graph structure. So how to add or remove edges. So what we think is this not only based on the original given graph structure. So by considering, by involving the node features, this can help us to better infer whether it exists a connection between two nodes. Since the one, so why the GCN-based model is outperforms the traditional machine learning model is it involves the node features, and then it can propagate these features through the convolution operation, right? And so borrow this idea. So in our case, to reconstruct the network structure, we can consider involving these node features, and to see we can build more scientific and more accurate graph architecture. Graph structure. So this is the intuition behind that.
I see. I guess another way of phrasing the question, I don't want to take too much time, is do we want to treat this process as like a topological black box? In other words, there's some topological quantity you can compute and it helps to make the result better, which is nice. Or is there some way to interpret what it means for this distance to be small or this distance to be large? Let's say, to explain to non.
Let me add in. So intuitively, the way how we saw it when we started this project is the following. Say, and that's what we put in the paper as well. So suppose that we are looking at matchmaking agency, yes? And so we are trying to match attributes. Two people submitted their series to information to matchmaking agencies. So each of them are nodes, yes? So they have certain attributes. They can have continuous attributes and they have categorical attributes, a whole bunch of those, yes? So what we can do is that we can simply match them based on the attributes, yes? That's one approach. There are algorithms that have been around for a long time where you simply look at the neighborhood of each node and then you aggregate those attributes, yes? Simply aggregating, or rather doing weighted aggregation. Now, the idea, what we are trying to do here is that we look at how peers of each of the candidates in this matchmaking agency, how they interact with each other, but not only social interaction, yes, but also in terms of their attributes interaction. So think about your peer network, your family members, friends. I mean, we can check, say, Facebook. So if we own a matchmaking agency and we have access to your Facebook and another candidate Facebook, yes? So then we look not only how often people in your closest neighborhood write to each other, but what is the interaction, the topology of their attributes, yes? That's the idea. So maybe your potential mother-in-law says something to whatever, all those things. And it's not simple aggregation anymore, of course. It's like the whole more sophisticated shape information that you get out of it. But that's the idea. I mean, clearly it shall work also for link prediction, yes, by an obvious thing, because it's how likely if two things, and actually it came from the idea of link prediction and clustering. So this is the intuition behind it. I mean, this is how I would explain to myself, I mean, why we're doing it, yeah? So it's not simply your attributes and somebody else's attributes, not simply aggregated attributes of your potential families, but how the interaction in a weird way, maybe you're watching the same type of movies at the same time point, or whatever.
That's probably true as well. Yeah, that intuition really helps. Thank you so much.
Further questions or comments?
Yeah, I can make a small comment here for algebraic topologists. So the main idea, this overly simplified idea is the following. So TDA, Pearson's homology, is we are trying to do node classification. TDA can attack by itself, or the graph neural network can attack this problem itself. So somehow you want to combine their powers. So first of all, by using Pearson's homology, we are trying to, so with the assumption that two nodes are similar if they had similar neighborhoods. Persistent homology can detect that. So when you do this, you give me an original graph and you take two nodes. If they are if TDA tells me they are similar, I am just gonna put an edge between them. If TDA tells me they are not similar, if there is an edge, I am cutting them. I am changing the whole graph, and epsilon1 controls which edge I'm gonna add. Epsilon2 controls which edge I'm gonna delete. So I am reshaping my graph to prepare for GNN and using STEM. And this guy tells me, and we are using distance-based Laplacian in the GNN. What we did is similar nodes, topologically similar nodes are close to each other now. And topologically dissimilar nodes are far from each other now by deleting this. So we are somehow we are trying to combine TDA power and the GNN power and to improve each other. That's the one of the way to look at this approach.
Thanks. More questions?
I have a question on implementation. Like, how long did the training take? Because we know persistence homology takes m cube time. So if you can give me a rough idea, and also the persistence layer you used, whether it's GPU based or it's done in CPU, that would be great if you can.
Yeah. So okay. So for the training our model, so for the small and moderate networks like Citation and the Power networks, it can be done on the CPU, and but for the OGB network, we need to conduct experiments based on the GPU, and also to generate the persistent diagrams. To generate the Watson distance based on the persistent diagrams between any pair of nodes. So here we consider, since we only consider the zero dimensional, and also the K neighborhoods, the K here we search from the 1 to the 5. So generally, for example, for the if I recall correctly, for the core ML, if we want to get the topological feature like Watson distance, it may take around the 5 minutes to get the whole topological information. And for the training for each epoch, it may take around the 1 second. Does that answer your question?
Yeah. Thank you. Thanks a lot.
More questions?
Hi, Yuzhou.
Hi.
I have a couple of specific questions. So going back to the question about epsilon1 and epsilon2, so does it mean that calibration of epsilon1 and epsilon2 actually depends upon the data set under study?
Yeah, exactly. It depends on you may different. The optimal hyperparameters may differ among the graphs.
Any chance to have like a heuristic on these parameters in advance?
Yeah, I see. I think it will be interesting to make these two hyperparameters as trainable weights in the model, and then we don't give a constraint for these two hyperparameters, and then we may can avoid to tune it by ourselves.
Okay.
It can be an explosion.
Did you try something else besides degree? I mean, you use degree. What else? I don't remember what else you use.
Yeah, we consider the filtration based on node degree and node attributes.
Yeah. Did you consider something else beside it? I mean, you have a bunch of measures over nodes that you could compute on graphs. There are so many of them. Why did you choose those? I
see. So at the beginning, we consider the node attributes as a filtering function. So since we want to involve more since in order to reconstruct the network structure, we want to involve more node features as information, right? And then we consider the node degree, since compared with the node attributes. So node degree is more easy to compute. But you are right. So in the future, we can consider other network statistics as a filtering function, like the closeness between these, etc. It will be interesting to see the performance based on different statistics as a filtering function.
Oh, okay. And also, you're using the Butterstein distance, so I am assuming that the exponent that you're using are, or I don't know, rho, whatever exponent you have there in the formulation. Yeah, P. Sorry, P. I'm assuming that you're using P equals to 2. Did you try any other value on P, but or do you expect to any changes used by changing that value or something?
Currently, we don't explore P here, but certainly we can tune the P. Maybe it can reflect the more accurate relationship between two nodes.
I would say that the results wouldn't change a lot, but yeah, who knows? I mean, I'm thinking about P going to infinite and then having the bottleneck distance, but that bottleneck distance usually sometimes get us into trouble sometimes. Yeah, I don't know. I mean, maybe there is something else.
I can make a comment here if you like. So basically you have two choices, 1 or infinity. If you want to count the noises, you want to count 1. You want to choose 1 because you want to also contribute. So you can have lots of noise which can contribute your Butterstein distance, or you can choose infinity. You just take care about the longest barcodes and the farthest barcodes. So we chose 1 because we are using degree and other stuff, and the noises in this neighborhood can be important. That's why we choose 1. And 1 and 2 and other family can be taught, but I mean, the major choice here, 1 and infinity. We chose 1 here because we see that the small but many noise features is important to detect the similarity between the nodes.
Oh, got it. And my last question, you are using this for classification. So Yuzhou, do you have something in mind that, I mean, is there any other application in which you think that you could use your well-rounded and developed framework?
Yeah, so we can certainly apply, for example, like the topology induced multi-graph representation, the conclusion from this framework to the link prediction, so that we mentioned before, and also it can be used as a material or the additional information for the adversarial attacks and or the perturbations. Since based on the conclusion from the topology induced multi-graph representation, so we can learn the similarity, I mean, in the topological space between two nodes, right? And if we would like to attack one node, attack one graph structure, so maybe we can borrow this information and the attack will be more efficiently.
Oh, got it. That sounds interesting. Thank you so much. Great presentation.
Thank you.
Well, thank you so much, Yuzhou, and thanks everybody for the interactive conversation. Let's end at least the recorded portion here. So thanks again, Yuzhou.
Okay, thank you.